Everybody pictures a black hole like some cosmic garbage compactor. You get crushed flat instantly. End of story. That's not what happens. What actually happens is worse and stranger and slower than that. Your body gets stretched, pulled out into a thread thinner than a strand of spaghetti, and depending on which black hole you happen to fall into, you could still be alive, still be thinking while it's happening to you. Let's actually follow the fall, second by second, because the real physics here is more disturbing and more interesting than anything the movies ever showed you. Here's the wrong instinct almost everyone starts with. You think black hole, you think enormous pressure, squeezing in from every direction at once, like being crushed underwater at some extreme depth. That picture is completely wrong. The thing that actually gets you isn't pressure at all. It's a difference in gravity between your head and your feet. Gravity weakens with distance. That's true everywhere, all the time, including right now, wherever you're sitting. Your feet are very slightly closer to the center of the earth than your head is, which means they feel a very slightly stronger pull. The difference is so microscopically tiny you will never in your entire life feel it. Near a black hole, that exact same effect becomes extreme, violently extreme, because the source of gravity is so compact, so concentrated, that a few feet closer stops being a trivial difference and starts being an enormous one. It's not a squeeze, it's a tug of war between one part of your body and another, and gravity always wins that fight. There's a real technical name for what this does to you, and it's not some cute nickname somebody made up for a documentary. It's the actual term physicists use, seriously, in real papers. Spaghettification. Your feet, closer to the black hole, feel a noticeably stronger pull than your head. That difference stretches you out, elongating you along the direction you're falling, while simultaneously squeezing you inward from the sides. Picture a grid of straight lines falling toward the black hole. The vertical lines pull apart from each other, stretching, while the horizontal lines get pulled together, compressing. Both happening at once, to the same falling object. Here's the variable most people never think to ask about, and it completely changes the story. It depends entirely on the size of the black hole you're falling into. A small, stellar mass black hole, one formed from a collapsed star, maybe 10 times the sun's mass, has such a compact, intensely concentrated gravitational field that spaghettification happens violently, fatally, long before you'd even reach the edge of it. You'd be torn apart while still, relatively speaking, far away. But a supermassive black hole, the kind sitting at the center of galaxies, millions or even billions of times the mass of the sun, actually has a gentler gravitational gradient right at its horizon, precisely because it's so much bigger. You could cross that edge completely intact, feeling nothing unusual in that exact moment, with the deadly stretching only becoming lethal much later, much deeper inside. Same physics, same mechanism, wildly different experience, depending entirely on which black hole you happen to fall into. Size here isn't a minor detail. It's the entire difference between instant and gradual. Now here's where it stops being simple. Here's where physics itself starts disagreeing about what you would even experience. And I mean that literally, not disagreeing in the sense of scientists arguing, but disagreeing in the sense that two totally valid perspectives give you two completely different stories. From your own point of view, falling in toward a large enough black hole, there's no dramatic flash, no wall, no signpost that says, event horizon, you are now crossing it. According to general relativity, you'd cross that boundary smoothly, seamlessly, feeling nothing unusual in that exact instant. Your own clock, your own sense of time passing, ticks along completely normally the whole way through. But here's the part that should genuinely mess with your head a little. To someone watching you fall from a safe distance, a friend back on a ship, say, watching through a telescope, you would never actually appear to finish falling in. Your image would slow down, it would dim, redden, stretch out in time, appearing to freeze right at the edge of the horizon, forever, never quite completing the crossing from their point of view. This isn't an illusion or a trick of the light. It's what gravity does to the passage of time itself, warping it more and more severely the closer you get to that boundary. Two completely different, completely valid descriptions of the exact same event, you falling in, depending entirely on who's doing the watching. And then there's the deepest layer, the part where I have to be honest with you and just say, we don't know. What happens after crossing the horizon on the way down toward the center involves physics we genuinely do not have a complete theory for. General relativity's equations predict a singularity at the center, a point of infinite density, where the math itself simply breaks down and stops giving useful answers. But when a theory's equations start predicting infinities like that, that's usually a signal the theory has run out of road, not necessarily a literal, accurate description of what's actually there. Quantum gravity, the theory that might actually describe what happens at that scale, where gravity and quantum mechanics both matter at once, doesn't exist yet, not in any complete, tested, agreed-upon form. Physicists have candidates, ideas, partial frameworks. Nobody has the finished theory.
So here's the honest state of things. We can calculate with real precision exactly what pulls you apart, and roughly when for any given black hole. That part of the physics is solid ground. We cannot tell you with any real confidence what's actually waiting at the center, because that question sits past the edge of physics as we currently understand it. Not past the edge of what we've gotten around to calculating yet, past the actual edge of the theory itself. Here's what actually stays with me about all of this, more than the stretching, more than the violence of it. Somewhere out there, right now, something is falling into a black hole, and depending on who's watching, the thing itself falling, or us watching from a safe distance far away, there are two completely different, equally true stories unfolding about the exact same object at the exact same moment. Relativity doesn't pick a winner. It doesn't say one version is the real one and the other's just an illusion. Both are real, genuinely, fully real, from where each observer happens to be standing. We like to believe in one shared universal story, the idea that everyone, everywhere, agrees on what happened and when. That time is one continuous thread we're all reading together. A black hole is the place where that comfortable assumption quietly, completely breaks down, where your own last moments and the universe's lasting record of you split apart into two different narratives that never fully reconcile, that never quite meet back up into a single agreed-upon account. You'd be stretched eventually into something no longer recognizable as a body at all. That part we understand completely, down to the equations, down to exactly when and how it happens, depending on the size of the black hole involved. But before that, in those final seconds, you'd be living out one of the strangest facts in all of physics, that your own experience of falling and the universe's memory of you falling are not the same story. And there is no version of physics today, not one, not even close, that can fully tell you what happens where those two stories are supposed to meet. That's not a small gap we're on the verge of closing. That's the actual edge of what anyone currently knows about the universe, and it's sitting right there, quietly, at the boundary of the darkest objects we've ever discovered.